Welcome to the Explainer. Today, we're going to build a mental roadmap that'll let you see the entire world just like a chemist does. And, our starting point is something you've probably got in your kitchen right now.
So take a look at this. Seems simple, right? It's just ice and water. But for a chemist, this simple glass is actually a key that unlocks a whole system for classifying every single thing in the entire universe. So here's our game plan. We're going to build this chemical roadmap from the ground up. We'll start with the big, simple questions, and then we'll dive into the details that explain everything, from why your bike might get rusty to why ice cubes melt in your drink.
Okay, let's jump right in. We'll start by figuring out what matter even is, and then we'll look at the first, and maybe the most important distinction that chemists make. It's such a simple idea, but it's incredibly powerful. Think about it. Everything from the chair you're sitting in to the air you're breathing, if it takes up space and it has mass, a chemist just calls it matter. And the whole goal is to be able to classify all of it. So whenever you look at anything, the very first question to ask is this: can I separate this thing physically? Like filtering coffee grounds from water, or maybe picking vegetables out of a soup. If you can't, then you're looking at a pure substance. If you can't, it's a mixture. And right there, that's the big divide. Pure substances, like pure water, they have a fixed, unchangeable chemical recipe. It's always H2O. But mixtures, like salt water, well, that's different. You can dissolve a little pinch of salt or a whole spoonful. The composition can totally vary. Okay, let's stick with those pure substances for a minute. The next question is, can I break this down using a chemical reaction, like with electricity or a lot of heat? If the answer is no, you've hit the absolute bedrock of chemistry. An element. If you can break it down, it's a compound. And this number, it's just astounding when you really think about it. The entire known universe, everything we see, is built from only about 118 fundamental elements. That's it. But from that tiny toolkit, nature has created tens of millions of different compounds, like water, which is just two hydrogen atoms chemically stuck to one oxygen atom. Now, let's jump back to mixtures. They also split into two types. You've got homogeneous mixtures, which are perfectly uniform. Think of a cup of tea after the bag is out. Every sip tastes exactly the same. But then you have heterogeneous mixtures, which are chunky and uneven, like a bowl of vegetable soup. Every single spoonful is a little different, a little surprise. All right, so now we have our categories. We can sort stuff into buckets. Now let's learn the actual language chemists use to describe what's in those buckets. And it all comes down to something called properties. This is a really crucial distinction. A physical property basically describes what something is right now, its color, how dense it is, its melting point. But a chemical property, well, that describes its potential, what it could become. Can it burn? Will it rust? That's a chemical property. This chart just illustrates the difference perfectly. So when gallium metal melts, sure, its form changes, but it is still fundamentally gallium. That's a physical property. But when iron rusts, it's not just iron anymore. It has chemically combined with oxygen to become a totally new substance, iron oxide. And that is a chemical property. Okay, let's circle back to our glass of ice water. We now know that ice melting is a physical change. Its form changes, but it's still H2O. But why does it change? Well, the simple answer is energy. This transition between solid, liquid, and gas is called a phase change. And here's the most important thing to remember. It is a physical change, not a chemical one. The H2O molecule itself doesn't break or change. It stays the same whether it's locked into place in an ice crystal, flowing around as water, or zipping through the air as steam. And energy is what drives all of this. Think about it this way. To melt ice, you have to put heat into it. That's an endothermic process. It's just like those instant cold packs that absorb heat from your skin and feel cold. But to freeze water, the water has to release its heat out into the cold air. That's an exothermic process, just like those little chemical hand warmers that release heat to warm you up. And a really fantastic, dramatic example of a phase change is sublimation. Dry ice, it doesn't melt into a puddle of liquid carbon dioxide. No way. It turns directly into carbon dioxide gas, which is exactly how you get that classic spooky fog effect you see at concerts or on Halloween. Now, here is a question that really gets to the heart of how phase changes work. Let's say you're adding heat to a beaker of ice that's sitting right at 0 degrees Celsius. what do you think happens to the temperature? Does it start to climb up right away? So the surprising answer is no, it doesn't. The temperature of that ice water mixture stays locked in perfectly at 0 degrees Celsius. All that heat energy you're pumping in isn't making the molecules vibrate faster, which is what temperature actually measures. Instead, every single bit of that energy is being used for one job and one job only, breaking the bonds that hold the water molecules in their rigid ice crystal structure. And this phenomenon creates what chemists call the phase change plateau. If you were to graph this, you would see the temperature of the ice rise up, then go completely flat while it melts. And only after the very last bit of ice is gone does the water temperature finally start to rise again. That energy is changing the state, not the temperature. It's a really cool concept. Okay, let's zoom back out and take a look at the big picture. In just a few minutes, we've basically built a complete chemical roadmap. So now you have this amazing toolkit. With just these few core ideas, you can look at literally anything: the air you're breathing, the coffee in your mug, a diamond on a ring, and you can start to classify it and understand its properties, just like a chemist would. So, we've given you the map, a whole new way to see and categorize the world around you. Now the journey of discovery, well, that's all yours. What will you investigate next? Thanks for watching.